Wow, the balcony is decimated today. The balcony is hey up there, balcony. A rough go up on the balcony today. Anyway, welcome. Thanks for coming out. I understand you have a calculus exam Friday, so I'll try and make this worth your while. What I promised to the first class is that on Friday I'm gonna shorten the amount of stuff we do. Like I'll make it a shorter lecture since you have Cal. If you plan on showing up, I don't know, you might not. But also since this is the afternoon class, you might want to show up to the morning section anyway if you plan on coming Friday. It's kind of rough to have to go to a class at 3:30, then write an exam an hour later or something like that, right? So I'll leave that up to you. This Friday is the one Friday we don't have this room. So this Friday, regardless, we're in NCB. But if you come, again, I recommend coming to the morning section if you can. If not, I'll be there. There might just be 5 of us, honestly. I don't know. We'll see what happens Friday. But anyway, I want to talk a bit about the midterm here. Well, of course, this thing's dead. So basically, we had a midterm, and honestly, I was very impressed. Okay, with what I saw from the midterm. To be honest, it was higher than I thought. Definitely quite a bit higher than last year midterm one. So overall, comment is well done. Learning this stuff. Clearly, you've been taking the time to learn it. On the same point, if things didn't go the way you want to, this is a full clean slate part 2 of the course. It's a non-cumulative second midterm. Please start taking advantage of stuff like the daily office hours where there's a TA there wanting to help and come up and chat with me after and make some positive changes to improve in part 2. Okay, so again, well done. I posted everything on I know what's happened. I'm so dumb. Is this frozen? I don't know what's going on. This is simply not working. Anyway, so I'm not sure what's going on here. Neither the clicker or the computer's working. Everyone can see that, right? I'm not crazy. It does say circuit elements up there. So I can see it, but it's just not moving. Okay, there we go. Anyway, so as I said, it's a non-cumulative, there we go. It's a non-cumulative second midterm. So it's a clean slate for everyone. Everything we do is kind of new. I also think this part of the course is the easiest stuff, especially this week, kind of circuits, once you've seen this kind of stuff before. There's definitely some difficult topics, don't get me wrong, but it's less mathematically complex than part 1 and part 2. So as I said, Friday lecture this week to accommodate for the fact that you have your calc midterm, it's going to be abbreviated. Even when I post online, I'm going to cut down what's associated to Friday's class because of your calc midterm. Another thing I wanted to mention to start the class here, next week I'm going to run an info session on something called the Engineering Physics program here at Western, so I'm just going to take a minute to talk about the basics. So I think it's a really great program for engineers. I mean, a lot of engineers are kind of have the heart of a physicist, but went in engineering because of family pressures or career perceived benefits or stuff like that. There's a really nice program here at Western where you get both a engineering degree, your BESC, and a physics degree from the Faculty of Science. So you graduate with 2 degrees, and it's only 1 extra year, kind of like the Eng Ivy program or something like that. So how it works is you take whatever engineering program like you plan on doing, plus you do the physics or astrophysics or medical physics major program here. Typically a major in the Faculty of Science is 6.0 credits, but we're allowed to double count 1.0 with your Eng program to bring it down to 5.0 credits, which is roughly 1 full year of studies. And then you spread that out over your 2nd through 5th year. So you'll take 1 or 2 physics courses per year. It's a really great way because you'll find in 2nd year engineering becomes super applied. you start to really just be, how do we do this? How do we do this? Not a lot of the why and kind of the interesting stuff behind the physical theory. So you can learn both through this program. And what we find is that graduates in this program are usually ones doing the coolest stuff. They're designing satellite dishes, building satellite dishes, working in the telecommunications industry, nuclear engineering, a lot of the really interesting things at the hybrid of engineering and physics is where you can find these grads. So anyway, I'll post an announcement. Hope to see you there next week. You have a question? Yeah. Say that. Do I teach any upper year? Not right now, but that's the plan in the long run. I just got back to Western about a year and a half ago, so I'm just building up these intro courses first. Then I hope to take, usually I teach something like electromagnetic theory. I mean, I'm kind of doing that here, but the more advanced one in upper year. Relativity, so like special general relativity type stuff, or classical mechanics, right? And usually what people do, if they're in mechanical engineering, they'll probably pair the physics courses they take with more of the mechanics type stuff. Or if they're in electrical engineering, they'll pair. So you can tailor the degree a bit to whichever you're doing. Anyway, so let me know after class if you have questions too, but I'll post on that. Anyways, last class, we talked about Kirchhoff's laws. These are like the Newton's laws for circuit theory, right? These are the place that we go to develop some models for our circuits. So right now we're doing what we call DC circuits, which gives us a system of linear equations, kind of like when we did block and Pauli problems in mechanics. But later on, we're going to use these same laws to develop differential equations, that is circuit models where we need to solve some differential equation, and that will be done in part 3 of the course, so we're not going to do that now. Today is our last circuit lecture. So we're talking about these circuits like we did last class. We have Kirchhoff's laws, we have your loop laws, your junction laws for the current going in and out of some junction. Assignment 3 and tutorial 3 are heavily focused on this stuff, so you'll get a lot of practice through the assignment and tutorial doing some of these circuit problems. But basically, today's lecture, we're going to talk about the elements, batteries, resistors. We're going to talk about those individual components of circuits today. Then what we're going to go do on Friday is we're going to talk about conductors, like the wires themselves and the physical properties of those wires themselves. So conductors is the topic of Friday's lecture. A little bit of Gauss's law sprinkled in there, because it's another great application of Gauss's law. Okay, so this is the main ones we're talking about today. Resistors, capacitors, batteries, and switches. We're going to be mainly focused on kind of the physics of these things, the insides of them, what's going on, that sort of thing. But I'll say there are lots of other circuit elements. For example, inductors we'll introduce later in the course. But there's lots of different components that do different things. And many of you will take a circuits course here at Western and kind of learn how to package these together to do useful things in circuits. So resistors we're going to start with today. Now resistors, the potential difference across resistors is represented by what we call Ohm's law. That's this delta V equals IR thing here. So Ohm's law, super important, especially for using the loop law with resistors in the circuit. So we'll be using this a bunch throughout the course. So delta V equals IR. I'm sure this will be on the equation sheet. This is one of those ones you should just kind of know, like F equals MA, delta V equals IR for resistors, kind of one of our more common equations. The resistance R is in units ohms. And the key thing to know about resistors, they reduce the flow of current in the circuit. So if you put a resistor in a circuit, you're going to reduce the rate at which this current flows in your circuit. Various reasons we want to do this in practice, but this is kind of the utility of putting one of these things into your circuit. A lot of what we're going to do today is talk about how we can add these things as well as another element called capacitors. So basically, if you have some complicated circuit, you could have a ton of different resistors in it. Mathematically, we could represent multiple resistors such as these two here, as one equivalent resistance between 2 points. Okay, so if you see on this diagram, we have point A and point B. We have two different resistors. Mathematically, we can describe between point A and B as being equivalent to just one resistor that has some different resistance that we can add based on those other resistors. Obviously, this is not in reality. When you're in your circuit lab and you're building a circuit, you put one resistor and you put another one. They don't just magically fuse and become a super resistor. We still have different resistors in our circuit, but this can simplify things because we can solve problems where we treat these two as just being one by adding the resistances. So in series, if you have two resistances, R1 and R2, they just add linearly R1 plus R2. Let's talk about why that is. Well, it's because the potential difference from point A to B, that is the potential difference across both resistors, must be equal to the potential difference across the first resistor plus the potential difference across the second resistor. So you have to add those two delta V's to get the total delta V. Then what we can do is use Ohm's law. We can replace the delta V for each resistor, but we know if this is just one wire segment, the current has to be the same everywhere in that wire. So I is a constant value for both of those, but R1 and R2 are different values for each resistor. So we put in Ohm's law for each one, and we can factor out the common I. When we do this, we see that the delta V across the whole package is equal to I, the current through that one wire, times the sum of the two resistances. That is the logic from which we say, okay, overall from A to B, delta V is the current times some total effective resistance, which we call the equivalent resistance, okay? So if you have resistors in series, you can add their values linearly to get a total equivalent resistance. We did that here for 2. This works in general. Any number, you can take any number of resistors, 1, 2, 3, 4, 100. If they're all wired in series, you can simply add up their resistance values to get the total equivalent resistance. So resistors in series, pretty straightforward. You just add up all their values. Again, this is not reality. In reality, the circuit you made, it's not like your 100 resistors fuse into some super resistor. This is just a mathematical simplification we can do. Okay, what about parallel? What if we wire two resistors in parallel? Well, if resistors are wired in parallel, it turns out we can also add up their resistances somehow. But there's a different rule for how to do this. Why? Well, to be able to add these resistors, we don't sum the delta V's like we did last time. We have to make use of the junction law. We know the current coming in here will be equal to the current flowing through this wire plus the current flowing through this wire. So if you have some I1 in this wire and I2 in this wire, then I equals I2, I1 plus I2 is going to be the junction law here. And that's the same current, that I, that exits on the other side of the other junction. So we can use this junction law to figure out how to effectively add these resistors such that we can write them as an equivalent resistance between those two endpoints. So we have point C here, point D here. We want to say these two resistors in parallel is effectively the same thing as one resistor here. How do we do that? That's kind of the question. So we start from the junction law, and again we go back to Ohm's law. Ohm's law here, we can rearrange for the current for each of the resistors. Now, these are different currents now. These are not the same current. so we cannot naively factor them out. We have to plug in those current relationships to the junction law. And then we have this expression here. The key thing, the key fact about wiring these things in parallel we have to use is that the delta V across each of the resistors must be the same delta V. Okay, this follows from stuff like equipotentials, which we'll talk about on Friday. But basically, the delta V across both of the resistors in parallel has to be the same value, so we can rewrite it as just delta V CD, which is the potential difference across the whole combination of resistors. What we can do then is we can plug that in here and have the same delta V, factor it out, and see how things add. So it's kind of like before. We plug in the delta V, factor it out, we see that I equals delta V times 1 over R2 plus 1 over R1. We have the sum of these inverse resistances here. Now, if we had one single equivalent resistor with resistance RCD across our point CD, we would know from Ohm's law we would expect this relationship. So we can relate 1 over RCD to this summation here to see how the total equivalent resistance relates to our different resistors in parallel. What we see is that in parallel, these resistors combine inversely. So 1 over the effective resistance is equal to 1 over the first one plus 1 over the second one. So in series, they add linearly. In parallel, they add inversely. And this rule is true for any number of parallel resistors. So it doesn't matter how many you have, the equivalent resistance of any number of parallel resistors, or 1 over that, is equal to 1 over the first one, plus 1 over the second one, plus 1 over the third one, etc., etc., etc. So we can take the inverse of both sides of this equation to isolate for REQ. REQ is that sum to the -1 when we take that inverse. So this is the law for how we would add resistors in parallel. So we have resistors in series, resistors in parallel. That gives us 2 laws, and I'll definitely give you these on the equation sheet. You'll have to know which is which, definitely. But we have 2 laws here for how to add resistors, one in series, one in parallel. Now, we can only use the parallel one for a parallel combination. We can only use the series one for a series combination. But if we have a huge combination of both, we can one by one use these laws to simplify things until we eventually get one equivalent resistance for a huge complicated package of resistors. Okay? So we're going to do an example showing what I mean by that. But this process here, and it's also under assignment 3. Assignment 3, the first question, is using these for a couple different resistor combinations. Okay, so we have this complicated combination of resistors. We have these 2 in parallel. We have one here, and we have one here. So right now, when we look at this, there's no 2 resistors that are directly in series with one another. So we can't start by using the series law. What we have to do is we have to look for somewhere where 2 or more resistors are 1 by 1 in series or 1 by 1 in parallel. And that we have here, these 2. We go into a junction, split up, recombine. These 2 resistors are wired in parallel. So what we can do is use the parallel addition law to combine these 2 into one effective resistor and then simplify our diagram accordingly. So you have here these 2 parallel resistors. One has 90 ohms, one has 45 ohms. So 1 over the new one equals 1 over 90 plus 1 over 45. You just plug those numbers in, rearrange, and get 30. So these have an effective resistance of 30, and we can simplify our diagram by rewriting those 2 as just a 30 ohm resistor. Now that we've done that first simplification, we see that our effective resistor here and this one are in series. We can now use the series addition law for these two. That one's super simple. 10 plus 30 is 40 for the series addition. You just add them up. So we can rewrite our diagram again. We have effectively 40 ohms of resistance on this side of the wire. 25 is still on this side. Now we have two resistors in parallel. We can use the parallel addition law to combine 40 and 25. So we do 1 over 40 plus 1 over 25. That's going to give us 1 over the effective one total, which is 15.4 ohms. So that thing we started with, it's a bunch of resistors. For calculation's sake, we can consider all of it together as having a 50 ohm resistance, okay? So it's fairly straightforward once you get the hang of it. Yeah. Say that again. Start the wrong order. It'll be incorrect. Because we can only do the parallel law for a parallel combination or the series for a series combination. But if you try and do like one that's in parallel with one that's later in series, it'll mess it up. And I think you could try this one. You can say, hey, I'm going to do those first, then I'll do this, and you'll end up with a different number than 15.4. All right. Power. We'll just briefly talk about power. Power is the rate of doing work, right? So it's the time driven work. SI units watts. So the work done by a resistor is Q times delta V. Okay, so the work done by a resistor is Q delta V. And basically, we need to take the time derivative of this to find the power. So if we take the time derivative of this, and delta V is some constant across the resistor, we can factor out that constant. We have the Q dt, which is what we call the current. So we find the power, or the power due to the work done by a resistor is delta V times I. This is the power dissipated by a resistor. So resistors, they would dissipate power or energy from the system in something like thermal energy or heat, right? So your resistor would heat up, it would let heat out of the system, and you can calculate it using this equation. We can also use Ohm's law to get rid of V or get rid of I and get some equivalent expressions. So delta VI, I squared R, delta V squared over R. These are all equivalent ways we can find the power dissipated by a resistor. Final topic on resistors is resistivity. This will come up again on Friday, but I wanted to touch on it here because it's kind of important, I guess. So resistivity is like the general property of the material that we use to develop resistance. Resistance is like the bulk property, like mass, whereas resistivity is the microscopic quantity, like density. That's kind of the relation. It's a bit different. It's not the exact analogy, but it's the basic idea. Resistivity, which we call this little rho here, is the property of some material. So it can tell you how resistive a material is, irrespective of its geometry. Okay, so when we talk about resistance, we're talking about a little resistor circuit element that depends on its shape and size. So the total resistance is the resistivity times the length of the circuit element divided by the cross-sectional area of the circuit element. So I have a nice diagram here to talk about this. Resistance is the property of the whole element. This whole thing is a resistor here. It has resistance R. This thing has a cross-sectional area a length L, and the material has some resistivity rho. So if we want to find the total resistance, we multiply the resistivity rho times the length divided by the cross-sectional area. Okay? So what's the important lesson here? Resistors, it's not just about the material you use, it's also about the geometry of your resistor itself. So if you make the thing longer, you have a bigger resistance. If you increase the area, you have a smaller resistance. There's more area for it to flow through. So you can change the geometry of your object here and impact your resistor without changing the material that you use. You might just have one material, but you might want different resistances to build the different shapes and sizes of your resistor accordingly to account for that. Anyway. Next element, capacitors. So capacitors, another super common one we're going to talk about in this course, especially in part 3 of the course when we talk about RLC circuits. Basically, a capacitor stores energy which can be released into the circuit, but it does not provide a source of energy such as a battery. So if you have a capacitor, you need to charge it, and then it can later dissipate that energy if you stop charging. How do we charge a capacitor? We use something like a battery. So you could plug up a battery to a capacitor in a circuit, charge it up. You can take the battery out, then that capacitor would release energy into the circuit. This is a dynamic process, which is why it's part of part 3 when we do dynamic circuits. But the capacitors themselves we'll talk about here. When you charge the capacitor, the total charge Q stored in the capacitor is equal to C, something we call the capacitance. So this is a property of the capacitor, basically its ability to store energy, multiplied by delta VC. That's the potential difference across that element. So it stores energy. What's the energy? This value here. The energy stored by the capacitor is 1/2 C times delta V squared. Okay, so this looks like a lot of the other energies we've seen, 1/2 mv squared, 1/2 kx squared, etc. We'll see more in this course. And the basic reason for that is actually quite interesting. When we introduce you to introductory physics, we want to keep things as simple as possible at first. What is simple as possible? Linear equations. We know force and energy have a calculus relationship, derivative integral. So if you take the derivative of energy, you get the force. The force is how we define the equations. So if it's linear, we will have a linear contribution. So if you take the derivative of 1/2 something, constant something squared, you end up with just the constant times that something linearly afterwards. So that's why a lot of our intro physics, you keep saying 1/2 something, 1/2 constant something squared, because quadratic energy is associated with linear force, linear equations, and stuff like that. Anyway, the basic idea, when the capacitor is fully charged, we have the delta V across the battery is going to be exactly equal to the delta V across our capacitor if we just have those two elements. All right, what about addition? We can also add capacitors in series and in parallel. So we can, if we have a bunch of capacitors, just like we just did, if they're in series, we can add them. If they're in parallel, we can add them. The important point, these laws are backwards to the resistor ones. Okay? Whereas resistors in series added linearly, capacitors in series add inversely. Whereas resistors in parallel added inversely, capacitors in series add linearly. Okay, so these laws are opposite to what the resistor addition laws were. Other than that, it's the same process. I'm not going to make you go through how to find these ones. I'll just explain it because it's pretty straightforward. Ohm's law is delta V equals IR. The capacitor law is delta V equals Q divided by C. Because the delta V for resistors is proportional to R, and for capacitors is proportional to 1/C, you end up flipping all the addition laws when you work them out. So you can do that yourself. You've seen that all the logic flips because of that. All right, on to batteries. So batteries, in this course, unless otherwise stated, so pretty much all the time, we're assuming that we have what we call an ideal battery. So ideal batteries are batteries with no internal resistance. Okay, so real batteries, like the batteries I put in this microphone here, or the remote, because I thought it wasn't working. Real batteries have some internal resistance to them that you have to account for in your calculations typically. We're not going to do that. We're going to say they're ideal batteries. They're simply providing a source to our circuits. Okay. So we have these ideal batteries. Let's talk about the physics of them. So here we have a battery connected to some wire here. Why? The question we ask ourselves, what is a battery doing? Why does a battery make the current go? Okay? So basically, what a battery does is it takes charges, so here we have a positive charge here, and it applies some force. That's this Fn here. Could be like due to chemical energy in the battery. And the basic idea is it wants to force all the positive charges to one end, all the negative charge on the other end, such that we have an electric field inside. The electric field will point from the positive to the negative terminal within the battery. When we create an electric field, remember, potential difference is an embodiment of the electric field. So even though for circuit theory we use delta V, delta V, delta V, delta V, deep down we're still talking about the electric field, because delta V is just the electric field integral. So if we create an electric field here, we create a delta V across the battery, and that ends up creating an electric field in the wire from positive to negative end here that causes forces on the individual charges. It's still F equals QE. It's still F equals QE. The force on a charge in an electric field is QE. So we need an electric field to move our charges, to go through our circuits, to power all the stupid stuff we do with technology. Okay, so that's kind of the basic idea here. The battery separates the charges, creates a potential difference, allows things to flow. Daily gift. It's nice to have motion again, right? Back to some gifts, right? Any daily gift fans here? No? Nice. It's a biased sample size. You're here when you have a calc exam, so I know you're down with the gifts, so let's go through some nice gifts here. These ones are nice. These ones are nice because this is a common analogy on how to think about a circuit. Think about, you know those artificial waterfalls where there's like a pump that pumps water up, then the water goes down, maybe it goes out of a dolphin's mouth or something, and then into a pool, and then you throw change in. Maybe you don't know what change is anymore if you didn't grow up with it. There used to be these like metal currency we would use to pay for stuff. Anyway, this is a nice analogy to think about how circuits are working. It's not the best analogy, but you can think of us pumping water up a waterfall and then letting it flow down. And when it flows down, it does something kind of like when back in the day, again, I'm really dating myself here, I wasn't alive in the 1800s, but when you had to mill flour, back in the day you typically had a mill on the water, and it would turn and it would grind the wheat into flour. Anyway, you can look it up. Believe me, it happened back in the day. Now they just, I don't know, engineers do something. But basically what happens, the battery is kind of like what the pump is in the water example. The battery forced the charges up the hill. The charges don't want to do that. The charges want to go in the opposite direction. But the battery forces them to go where they don't want. Then they go around until they hit some element in our circuit where we then decrease our potential difference, and in the process make something happen, like turn lights on or some crap like that. And it just goes around and around like this. Like, so it's a nice analogy to think about, yeah.
Now is this done using
Okay, like we talked about, a good question, the electrons flow in the opposite direction. So the electrons would be the complete flip logic. This is based on conventional current theory, which is that it goes out of the positive and back into the negative. More appropriately, we would design this in the flip step side with negative charge going, but we teach it with conventional current theory. I prefer to do it with electrons as a physicist, I'd say. So let's look at some other ones here. Well, what happens then when we have parallel? This is a good one. It's a really good one. Thank you, Science Joy Wag. 1998. Holy. Is that when all you were born or so? That's a long time ago. See, gifts have been around for a long
9
time.
years.
I was definitely alive then. You might not have been, but anyway, we have a parallel circuit here. Our battery pumps it up. When we get to the split for the parallel circuit, less of the charge is going to want to go through the heavier resistor. So more of the current flows through the lighter resistor. So this is what's happening when we calculate those linear systems. What's the current in this wire? What's the current in that wire? We're figuring out how much charge is flowing through each of those branches of our circuit. If we were to remove one of these, we've got a short circuit, all the charge would flow through it. Finally, we have one other nice one here. What if we had two resistors in series on one of our parallel branches, and all of these R values are the same? Well, we would use our resistor addition law to say that this branch effectively has twice the resistance, so less current is going to flow through it, more flows through the other branch, and this is, anyway, I wanted to share these gifts because I think they're a nice way to conceptualize what's going on. It's very difficult to put your head inside of a circuit. Don't try that literally. I don't want you to electrocute or something. Anyway, let's get back to the lecture here. Okay. What else do we have? Well, there's power delivered by the battery itself. It's a similar situation. Work done by the battery work done on a charge by the battery. This is charge times the EMF of the battery. That's the battery's delta V. This is identical to the resistor case. We can plug it in, factor out the delta V. We're left with EMF times I as the power done by the battery. If we just have one battery and one resistor, those powers must be equal. What does that mean? It means any power given by the battery is taken by the resistor, which should make sense, right? We put energy into the system with the battery, the resistor takes the energy out. I think we have a nice example here that is a light bulb. So a light bulb, we can actually model like we do resistors. So essentially when current flows through a light bulb, that the power expressions we develop for resistors are ones we can also use for light bulbs. So here's our power expression for the resistor. And we're going to calculate the current due to a common household setup. So let's say it's a 60-watt light bulb. That's a common one you buy in the store. And it's connected, the lamp is connected to some standard 120-volt outlet. So if you were to calculate the current in the circuit for this situation, you would just plug in the power, which is that wattage of the bulb you bought, divided by the delta V of the wall outlet, and you would get 0.5 amps of current being drawn through this circuit. So that's kind of a basic household example. And for light bulbs, we can really use our resistor theory to describe a lot about what they're doing. The difference with the light bulb is, instead of just emitting heat, light bulbs, of course, emit light, right? And that's kind of one of the fundamental differences there. Okay, what about switches? So Here we're going to introduce a new element and talk a bit about light bulbs. So we have some switch here. This switch can be closed or open. If it's open, current just flows in this one loop. If we close it, we have current flowing in two loops, two circuit loops. Switches are obviously a common household thing you have, but also important when we talk about physics problems. We can do stuff like say, at time t equals 0, we're going to close the switch and see what happens. And we're going to do that a lot in part 3 of the course. So let's talk about this. There's just one current in the circuit. This battery is powering them both. These two light bulbs, they would have the same current flowing through them, so the same brightness. Now we're going to talk about the situation where we close the switch. So when we close the switch, now the effective resistance is going to drop due to our parallel situation, but the current is also going to increase in other places. I think this actually makes more sense just showing the diagram first. Let's look at this situation here. So we have this is the same circuit. This is our light bulbs represented as resistors. And we're going to talk about the open and closed case. When it's open, we could use Kirchhoff's laws, or just the loop law in this case, to solve for the current. That's epsilon over 2R for both of these bulbs. So when it's open, both of our bulbs have the same brightness. Now we go and close the switch. When we close the switch, we know from the junction law that the current is going to split up into two branches. And what we can do if these are the same resistance is we can use Kirchhoff's loop law and junction law and solve for all the currents. If we solve for all the currents, something interesting happens. Our battery is now providing a larger current to the system. So when we close this switch, the first bulb gets brighter, but the second bulb gets dimmer. Because the current is split between these two branches, the current we solve for here is smaller. So we have this interesting situation where one light will get brighter, the other one will get dimmer, and another one will turn on. And it's because we're kind of sharing the current between those two final light bulbs here and here. Right, so switches, they're very important in this stuff. You might have noticed this in your house before. If you have a bunch of stuff running, then all of a sudden you put on like a super power consumption thing and all the lights like go down a notch, right? That happens sometimes in my house. I wouldn't say the particular device I turned on, but it consumes a lot of power, and all of a sudden the lights go down, and I'm like, what's going on here? But I know what's going on because I have to teach this. Anyway, final topic here we're going to go into today is grounded circuits. Okay, you've probably heard of grounded circuits before, but I think this is one of the biggest conceptual misunderstandings people make when they learn this circuit stuff. What do we mean by grounding? Why is this so tricky? Because different people mean different things when they're referring to grounded circuits. If you are talking to an electrician or someone who develops devices based on this circuit theory, there's a couple things you might have heard of. One is safety reasons, right? We typically connect our household circuits to the literal ground, which is where the name came from originally, so we can avoid dangerous voltages that would electrocute people. So that's a reasonable reason, right? That's a reason we would want to introduce grounding. So we introduce grounding to basically provide this safety mechanism for our circuits. The other one is practical purposes. If we have different electronic devices, we can do this to set a common reference point between the devices to help make them be compatible. This is the type of stuff you would learn if you go into electrical engineering and work on some probably bigger than household projects, some kind of major construction projects or stuff like that. So here's some kind of practical reasons people talk about grounding. For our purposes, the reason we introduce grounding is that's where we zero point conventionally in circuit theory. Okay, so the word grounding when we're talking about our theoretical problems is the point where we want to set the potential equal to 0. Remember, that was arbitrary. We did infinity for point charges. We did one of the plates for capacitors. Well, for circuits, we define a ground location. That's going to be 0V. Every other point is relative to that 0. Okay, so it's just like before. Delta V is what physically matters. So that's why in circuit theory we always talk about, oh, the loop law, add up your delta V's and stuff like that. It's actually different here it's a different approach here. We want an isolated value for V at different points in the circuit. So we put a ground location as our 0 point. Doing this does not change the behavior of our circuit. It just specifies the 0 point. Okay, so the grounding location, even in safety applications, you're not always pumping current there. That's kind of a fail-safe if something goes wrong. In this case, our ground spot isn't doing anything. It's just a 0 reference point. So let's look at some examples here, or an example, I guess. Let's say we have this circuit on the left. Okay? We know what all the delta V's are. Delta V here is 4. Delta V here is 6. Delta V for the battery is 10. So we know from our loop law, we would go up 10 volts, down 4, down 6, we'd get back, and we would have the sum to 0 from our loop law. When we introduce a ground, and that's what this symbol is here, this weird little symbol attached to our circuit, we specify that any point here until we reach an element is at 0 volts. Remember, we're assuming ideal wires. On Friday, we'll talk about why this is. It's something called equipotential. If you have an ideal conductor, every point in that conductor in equilibrium has the same potential. So if we ground here, we have 0 volts here, 0 volts here as reference points. Okay? So, if we want to find the voltage right here, in between the resistors, we know that this resistor has delta V of 6, so we can say that here we have 6 volts relative to our 0 point. What about right here? Well, this has delta V 4, 6 plus 4, we have 10 here. According to our equipotential rule, that has to be the same potential as we have over here. The same logic works out in the other direction. We have 0 volts here, we go up 10 volts from the battery, so we have 10 volts at any point over here. Okay, this just allows us to pick any point in our circuit and define a single numerical value for the potential, which is going to be relative to our grounding location. Anyway, if I don't see you Friday, good luck on your calculus exam. Hope it all goes well, and we'll